Okay, got it.
Just if you bring your tablet in and you connect to the Zoom meeting that you're in right now, record on your tablet.
On my tablet, okay.
That's a something you do. Use it as.
Yeah. Alrighty, so we're good now. We're rocking and rolling.
What?
Okay, so on Blackboard, you should see in this week's assignments, you will see a 1/r² activity as well as the weekly evaluation. You are likely to see those added to. That 1/r² activity is very much like a laboratory, because what you're going to do is you're going to look at sound intensity and how it falls off as 1/r². So, yes, it's sort of like a lab, but it is part of the in-person class activities, which is separate, okay? So you're going to do a 1/r² activity. We'll talk a little bit more about it on Wednesday, but it is already there if you want to start looking at it. The other thing that you're going to want to have, and most of you already have it because of how we do things. If you go to your 5-box, in your 5-box you do have an audio spectrum and an audio scope and an audio amplitude. Okay, that is a sound meter, so you will be able to record using your 5-box. You also have a Doppler effect, and guess what? You're probably going to have to do it. Probably going to have to do a Doppler effect one as well, so you will have that in here as well. Now, you also have a tone generator. Just be aware that those are there. This particular app, Sound Meter app, it's free, and you can get it for both the iPhone and yes, you got to deal with the lovely ads, but it is also a decibel meter. But I used this one to verify. I have a friend who's an industrial hygienist, and we were doing an audio survey of a workspace and a work floor. This one actually goes very, very well with the calibrated decibel meter that he had for industrial hygiene. So this one also works extremely well, and so those, you can use it either way. When we get to that sound intensity, 1/r², and your Doppler effect one, you'll want to use the 5-box one when we get to that one. That one will come out next week. So you'll want to, you can start looking at those ahead of time. So yes, so there's a little bit of differences going on this semester because we have an in-person person, which is great, which is wonderful. And even given that, I'm still running around. So those lives are there. Also, since I have more of you in here than what I have in Thermo for the Rockets, I understand that there has not been a scheduled time to have the Rocket team meeting, and because of that and trying to get things done, I made a command decision that we will do our competition in the spring rather than try to get it finagled for this fall. But we do need to meet, we still need to get things going because we will still be participating in High Frontier, and because we need to do that for our volunteer efforts and things like that. So once you guys settle on a time, okay, any time afternoon and before 2 on Tuesdays are generally good, just not tomorrow. So if you guys want to coordinate a time to get there, and my Thursday afternoons are generally pretty well open as well. But I just couldn't see how we were going to be able to finagle it off with the school starting schedule for some of the faculty that we were dealing with, the people that I was talking to. If you want to participate in the Rocket team, please let me know. We will be kicking off our science club here shortly, and we are going to be kicking off the Native American club as well. This is likely to happen after Labor Day at this point. So if you're interested, please, 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 and I will make that announcement for my pre-engineers as well. in Intro to Engineering. Speaking of that, some of you participated last year in our pre-professional workshop. We are doing that again. It will be September the 5th here on the Tonkawa campus. I would encourage you all to participate. I will post the registration form for that, but what we typically do at that meeting is we talk about resumes, we talk about internship opportunities, we talk about some, I try to have the IRE Bell program folks come in and talk to us about what's going on. We've had the rural scholars come in and talk to us as well. So we talk about a variety of things that we can be doing to enhance your educational activities. So I will post that in Blackboard so that you guys can get all of that as well. So questions about what's coming, upcoming, things that are the extracurricular type stuff from the guys in Enid doing okay? All right. Okay. Also, just as an information, I will be here for my Intro to Engineering class. Then tomorrow morning I do my office hours in Stillwater, and then I'm back up here on campus tomorrow afternoon. But I'm in meetings all afternoon tomorrow. All right. I don't want to play with the buttons over here, so we're just going to go with it. One other tidbit, I don't know if I showed you guys it or not. One of the cool things that AI does is if you have a YouTube video, you can go into your AI app, whatever one you want, and take that link and have the AI create you a video summary. Now what's nice about that is that it gives you the timestamps for what's in the video. So if you go back to my old playlists, and I have a Physics 2 playlist, and the reason I combine both general physics and engineering physics in the same playlist is it really doesn't matter whether you're doing physics algebra based or physics calc based when you're talking concepts. Doesn't matter. The Doppler effect is the same whether you're doing algebra-based physics or you're doing calculus-based physics. Things that are different, there are some things that are different. But concept-wise, there's no difference.
Right.
So you can actually go into those old videos. Now the newer videos, when I am posting them, and you will get a Engineering Physics 2 playlist for this fall specifically, I have been going in, running the summary, and posting those in the comments. So that if you know down the road, when we do the Doppler effect, you can say, oh, she's worked the Doppler effect at 10 minutes into the video. So you can jump right to that time point. So that is one of the nice things that is out there. So if you haven't discovered that feature, it's a really slick feature. Now I do it with Gemini because Gemini is my preferred. Just so you all know that that's my preferred. All right, so we had been talking about simple harmonic motion. Let me get my lovely piece here. And there were a couple of things that I didn't want to do off the top of my head on Friday. Because by that time on Friday afternoon, it had been a week. And we all know that through the week I do tend to lose a little steam. So we had done our equations of motion for simple harmonic motion. We get, I'm going to go ahead and do y as a function of t because if you're doing a bouncing spring, you're looking at the y direction. Also, your book does it as well. She does it as y max, cosine omega t plus our phase angle. Remember that y max is going to equal our amplitude. We also went back and looked at our models. The three models that we looked at were the pendulum, the circle, and our bouncing spring. Those are our three models that we use. And this relates back to 2 pi times the frequency, and remember the frequency is 1 over the period. So if I'm dealing with a pendulum, that's what I'm dealing with. Now, we know that velocity with respect to time is going to be our derivative with respect to time, and then we get a minus y max omega cosine, or whoops, sine omega t plus v. And that's our velocity equation that we deal with. And then we can get our acceleration, which is our derivative with respect to time. And we get our minus y max omega squared cosine omega t plus v. All right. The one thing I didn't want to do off the top of my head, because I didn't want to screw it up, so I brought in my notes. If we do the sum of the forces in the y direction with respect to t, this is going to be our mass times our acceleration with respect to t. And if I do this, picture, okay. And if I do this with related to Hooke's law, right? Related to Hooke's law, you get negative k y. Okay? So all I've done is put Hooke's law. I did put the negative sign in because it is a restoring force. Now you're also going to understand now why they want you to choose the cosine function rather than the sine function. Because if I rewrite this, I get MA is equal to minus KY. I get M minus Y max omega squared cosine omega t plus V is equal to minus K Y max cosine omega t plus V. Y maxes cancel, my negatives cancel, my cosine omega t's cancel. I get mass omega squared is equal to K. Omega is equal to the square root of K over M, where both of these are from our physical system. Which is a pretty cool result. So your angular frequency is going to be related to whatever your spring constant is divided by the mass. And if I'm dealing with crystalline structures and we approximate that covalent bond as a spring, which when you guys get to organic chemistry, if some of you choose to go on to organic chemistry, you're going to find out that's how we do infrared spectroscopy, if we look at those vibrations. So this idea of simple harmonic motion or vibrations or oscillations, depending on how you want to phrase that in your books, you can come back with the mass and the spring constant come into play. Just to remind everyone how to calculate spring constant, I can have a graph And if I do a force versus position graph and I get a slope, the slope is the spring constant, right? Or if I've got F is equal to mg, if I'm dealing with a spring, and this is equal to kx, and we're dealing with magnitude. So if I have my spring, and this is a 50-gram mass, and we did our stretch, my initial is 10 centimeters, my new one is 15 centimeters, x is my stretch, that's 15 minus 10, and now I'm going to get my 5 centimeters, which is my 0.05 meters. K is equal to mg divided by x, so I'm going to be in Newton meters, which is what you end up getting. So I get my 0.05 grams or kilograms, 9.81 meters per second squared, which gives me my newtons, and I get my 0.05 meters. Oh good, I don't have to do any calculations because those two cancel out. And I get Newton meters as my spring constant. So you don't forget, you can actually calculate your spring constants for your experimental setups. And you can get those taken care of. So just a little bit of a reminder as to how that all works. We also talked about on Friday, looking at the energy, potential energy of a spring is kx squared. And then you also have your positional potential energy depending on what you got going. Okay. So that's where we were with a little bit of extra. But I want to take us to the next level. There are reasons that I beat on you guys about certain things. One of those things relates back to the simple pendulum. So there's my simple pendulum. We make two assumptions in my simple pendulum. One of which you can't really test. You could if you wanted to, but you don't really test. But we make two assumptions related to the simple pendulum. One was the fact that I do this at small angles. So we make the small angle assumption. And there's a lot of reasons why we talk about the small angle assumption. There's a lot of reasons that as we start getting into electricity and magnetism, we're going to be making certain assumptions because it makes the equations look a lot prettier and I don't have to mess with it. And the assumption was that my angle and the sine of the angle are approximately equal, provided that my angle is less than 20 degrees. And you can go look at your mathematics tables, plug it into your calculator, make yourself life really good and all kinds of happy. All right. Another assumption, although we don't do the small angle assumption, but another assumption that we're going to deal with for a lot is if I have 1 over r, and r is approaching infinity, this essentially goes to 0. Okay? And we will end up, and then it doesn't matter if I do 1 over r or if I do 1 over r squared, it's going to go the same way, it's just going to get there faster. Right? It's just going to get there faster. But when you start doing integration and you're using those boundary integrations, that's a term that all of a sudden it can go poof, and I no longer have to carry that term. We don't have to carry that term, and it also gets us into the realm of what we were talking about in other classes, is that if I have got a curve here, and I am looking at this little teeny tiny space of my curve, this is where the calculus comes in. I can approximate that as a straight line. And the smaller that increment is, the better that approximation becomes. And that's going to come into play with our waves as we start looking at waves. Because as I start having a sound wave go out, this is going to look like a plane as it approaches me. And we call that the wave front. So as we start dealing with our waves, we're going to be making some of those lovely assumptions. And they work really, really well. They work really, really well. Now the 1 over r squared problem, you got to be a little ways away because infinity is one of those weird numbers, and if I'm right on top of it, I can't do a 1 over 0 because that's undefined, right? But I can do a 1 over a 0.000001. So you do have to be some distance away from your source because we get those singularities that cause us a problem. But that's so these assumptions that we use become important. The reason I bring this up is we have 2 other pendulums. We have what is known as the physical pendulum. And it turns out your leg actually works as a physical pendulum. And if you go into your textbook, they actually do that physical pendulum piece. Because one of the things I now have to deal with, if I have a physical pendulum, and if this is swinging back and forth, I have rotational motion. The simple pendulum, that mass is so big at the bottom that we can disregard the mass of the string that's holding it on, and I don't have to worry about the mass of the string because it's so small, it's not contributing to the motion, it's not causing my motion to change. And if we remember, torque was related to my moment of inertia times my angular acceleration. So when we deal with physical pendulums, you're going to have equations that look like this. My angular velocity is going to change related to mgr center of mass, because remember Newton is going to say that all the mass acts as if it's at that center of mass, divided by our moment of inertia. Because my rod has a different moment of inertia than my point mass. So if I did this as a simple pendulum, this would behave as if all the mass were sitting at where it is, that center, the R, the center of mass, and I'd be back to my normal item. And what you're going to see is that changes the period. Because remember, omega is equal to 2 pi over the period. So the period is now 2 pi over omega. But now I'm impacted by my moment of inertia of my rod. And if we think of a person, so I usually do this problem in my general physics class because I have a lot more medical types. You actually look at your leg, you have your thigh that's rotating around the hip, and you have your lower part of your leg that's also doing a rotation. Or you can make this an assumption that all of your leg is just one rod. But you can actually go in and get a better estimate based off of how you're going to do this rotation. You can also do complex ones. Think of a grandfather clock. I'm sure you've all seen some grandfather clocks that look like this. And they have a big disc here. And we can slide this disc up and down. Well, that's going to be a physical pendulum. It's not, most of your clocks, you think about it, they're not going to work like a simple pendulum. I do have to account for that moment of inertia that's out there. So you will see that change. So that's another one that you have to look at. And you have to be aware of those distinctions. There is another one. Actually, there's two more. I don't know if anybody's ever seen one that looks like this. I've got a disc at the bottom, and this is actually twisting. This is what's known as a torsional pendulum. And it's got simple harmonic motion going this way instead of the other way. So you do have that example. We see torsional springs out there. We utilize torsional springs, and actually you end up with an omega, and then you get this lovely equation that looks like this. And K, this is not our spring constant K, this is a twist K, and this K is called the torsional spring constant. And then this is divided by, again, my moment of inertia of the object that's on the bottom instead of mass. You'll also see another one that we haven't talked about, and you'll see them in watch springs. And these kind of behave like a torsional pendulum. They're a little bit more complicated. As this spring comes out, it opens up the circle, and it's going to behave more like that torsional pendulum. So you have lots of fun things that you can play with. Questions before we move on to pulses and waves? You guys good over there in Enid? All right. Okay. So I can take a pulse. So if I have a piece of string attached to a point, I can snap the string and I can let a pulse go down. And we know that what's going to happen is that pulse is going to travel down the string. We've all done it. We've all played with it. We see that pulse. Now this pulse, typically when we're dealing with general physics or engineering physics, we think of that pulse as our sine wave, right? If I look at how in my pulse, and as that pulse is traveling across, what's happening to this little mass increment, this little dm mass increment, is it's going up and down in place as that pulse moves through. Now what's what's interesting about that is that my pulse, while this is going up and down, and it's going to behave like simple harmonic motion, this has got its own character and it's going to go through. They're kind of independent motions of each other. You can think about it as I can have a buoy. There's another fun thing that you can play with. I can have the buoy attached to the bottom of the lake, and I can have a wake come through, and it's going to cause this buoy to bob up and down as that wake passes through the buoy. I mean, we've seen it, we do it, we play with it. But this pulse that goes through, we're going to look at it in terms of a string, but we see it in water. We see it in air. We see it in other liquids. You can even see it in plasticized and fluidized solids. All right, we typically call that a wave. It happens to be a pulse. A wave is usually a series of continuous ones. Because if I were to drop a rock in the middle of the pond, we know that we'll watch a wave crest. If that drop is consistent, we know that it will continue out. So we get waves. Now these are all mechanical waves. Mechanical waves have to have a medium. You gotta have a medium. It's gotta be a string, it's gotta be air, it's gotta be water, it's gotta have something. Mechanical waves are gonna have a medium. Now the other thing is, one thing we know about all waves, whether they're mechanical or electromagnetic waves, is they are going to transport energy. So waves are going to transport energy, and we're going to see those things happen. So if my pulse comes through and hits the wall, the pulse is going to reflect, and now it's going to travel backwards, upside down. So we do get reflection. And we see this all the time. It will bounce and it will come through. And what's happening is you've got waves are additive. Mechanical waves are going to add. I can take a wave like this. Okay, it's coming in. And I've got my pulse coming in this difference. As these two intersect with each other, they're going to be additive and they will double up. But at the end, they will pass through each other, and I will have that wave traveling and this wave traveling in that direction. So my waves are additive. This is called constructive interference. Now, I showed you that reflection coming through. If I have to have this reflection coming through, and I have this set up, which you can do it, you can set this up so that you have these pulses coming through at a regular interval, and I have my pulse coming through like this, and my pulse coming through like this, I may get a flat line. And I have my pulse coming through like that, and now my pulse is going back like this. This goes in here, this one comes out that way. This is destructive interference. So you can have constructive and destructive interference. So you can get those pulses. Now, this on a string, we've all seen it. We're all comfortable with it. We know that the things bob up and down. This we would refer to as a transverse wave. It vibrates up and down. Now, if I have an earthquake, I can have transverse waves. I can also have the other kind, we're gonna show you the other kind. I can just never remember which ones are P and S ones. They talk about primary and secondary. I just can't remember which ones they call the primary and which ones they call the secondary, but you can have transverse waves. Things that bob up and down like this. But the easiest way to think about it is if I have a wave that's traveling down a string, it's likely to be a transverse wave. My slinky is the best way to describe both types of waves because I can have my slinky and I can create a transverse wave with my slinky, but I can also create the second wave with my slinky. I can have where we've got rarefication and compression. So in my slinky, I can send this little compressed wave and it comes through and it's compressed and then it extends, it compresses and extends, it compresses and extends, and it's compression and rarefication. Rarefication says the density is going to get a little bit different, and these are called longitudinal waves. Now sound, if you go, do the puff, 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 puff against your hand, you're going to feel the air compress and rarefy, compress and rarefy, compress and rarefy as it comes through to your hand. Sound waves are longitudinal waves. They both can be described using our cosine and sine functions. We aren't going to have any difference using cosine and sine. That's we can still describe it that way. But our sound waves are going to be longitudinal. Waves in a string are going to be transverse. Both of them are going to carry energy. We can use the same mathematical construct to demonstrate what those are. And we can play with that as we move on. And our speed of our wave, the velocity of the wave, is going to be the wavelength times my frequency. Now if I have a transverse wave, this distance is my wavelength. One complete cycle is my wavelength. The time that it takes is my period. So my velocity is still going to be my wavelength times my frequency, or I can look at it as my wavelength divided by time. And that's the velocity of my wave. I'm not going to have too much difference there. All right. I'm going to stop there because I got 5 minutes left before everybody goes, ooh. And I want to make sure everybody has an opportunity to answer questions or ask questions.